Hello again, my dear students, and welcome back to the second part with our first lecture concerning the introduction to sensors. In the first part, we have considered the semiconductor perspective of a thermoelectrical sensor. Now we are going to turn into the circuit perspective of a semiconductor sensor. And if you remember in the first part, we already considered the concept of sensor on a chip. And we have mentioned that by the end of the day, we have to integrate each and every part of our small sensor in a form of integrated circuit. In this part of the lecture, I would recommend you to visit one of the Springer Nature book series under the title Precision Temperature Sensors in CMOS Technology, where we are going to consider some of its circuits as a part of our course. Okay, so let's start with one of the basic examples for integrated temperature sensors. Herein you can find the model. But before proceeding into this model, let's do some sort of refreshing for our knowledge about the basic element of this model, which is a bipolar junction transistor. So let's now go to our whiteboard and try to illustrate some basic concepts, or refresh some basic concepts related to the bipolar junction transistor. Okay, that's great. Okay, so if you remember, my dear students, bipolar junction transistors, or BJT, have the structure of this. We call this the collector, the base, and the emitter. Generally speaking, we have two types of bipolar junction transistor. It could be what we can call a PNP junction. So this is a P, and this is N, and this is P. In this case, holes are going from the emitter to the collector whenever the voltage on the base accepts this, where in this case, you have to put voltage on the emitter greater than the voltage on the base, or VEB should be greater than or equal 0.7. In this case, current will flow, or holes will flow from the emitter to the collector. And as you know, that the direction of the current is the same as the direction of holes. So you will have your arrow in this direction. So current is flowing from the emitter to the collector through the base. And this is a P region, this is a P region, and this is an N region. So this is the first model for a PNP BJT, or bipolar junction transistor. On the other hand, you can have the other side, or the alternative design, which can be an NBM transistor. So for an NBM transistor, you will have here is N, and here is N, and this is P. So in this case, electrons will move from the collector, from the base, from the emitter to the collector through the base. And in this direction, in this case, the direction of the current will be the opposite direction. So the current will flow from the collector to the emitter. So this is basically a very quick revision on what is a bipolar junction transistor. Now, one of the famous ways to implement a diode, a PN junction, using a bipolar junction transistor is to make this connection. By making this connection, so by connecting the base into the collector, you turn your device to be as equivalent as a PN junction. Let's say how and why. How it behaves like a PN junction and why we do this. Okay. First, how basically, when you are considering a bipolar junction transistor, you can see that this bipolar junction transistor is basically consists of a two p-n junction. You have a p-n junction between the base and the collector, and you have another p-n junction between the base and the emitter. And if you return back to your basic electronics modules, when you consider the bipolar junction transistor energy band diagram, you will typically find this 2p-n junction when you are considering different region of operation, either saturation or forward bias or reverse bias or whatever. So this is or inactive region and saturation region and all this stuff. So basically, this is the construction of a bipolar junction transistor. It's a combination of a 2p-n junction. Once we make this short circuit, then automatically we disable or deactivate one of these p-n junctions. Following that, we have the other p-n junction, which is now between the base and the emitter. So this is N and this is P. So this is typical NP or a p-n junction. And in this case, you can easily find that the voltage between the base and the emitter, which is the VPE, is typically equals to the voltage between the collector and the emitter, which is VC. So this is one of the very famous way to make a p-n junction using bipolar junction transistor. Now let's come to the next question. Why we did so? So whenever you need a p-n junction, let's do a p-n junction. Why should I do a bipolar junction transistor and then turn it to be a p-n junction? This is simply part of the IC technology. Because whenever you are going to make an IC technology, you have to have what we can say a coherent building unit. This coherent or this repeatable building unit is transistors, as you know. So transistor is a basic building unit in all analog and as well as digital electronics. So in this case, you are still using transistor, and by only shortcutting the link between the base and the collector, you turn your basic transistor, which is the building unit of your IC technology, to behave like a die. That's why we did this model, or we did this course. Now, let's turn back to our presentation slides for a few seconds. Here you can see. So in this case, in this basic transistor, as you can see, we have two transistors, two bipolar junction transistors. As you can see, the arrow is going from the emitter to the collector, which means that this is an P and P transistor. It seems that these two transistors are not identical. This is simply because when you go to the conducting current, you will find that there is difference in the conducting current. So here we have a current source which is terminated by I, and this is another current source with I multiplied by some ratio equals to P. So these are two not identical. That's why we have here VPE1 and here we have VPE2. As you know, we call it VPE. However, in this case, the voltage on the base is, the voltage in the emitter is greater than the voltage in the base, because this is typical a PNP transistor, but herein you can consider it as an absolute value or as a negative value as well, or with this negative sign. So now we have VPE1, VPE2, and there is this difference between them, or the difference between these two VPEs are noted as delta VP. The question is, how this schematic behaves or should behave like a temperature sensor? This should be answered in the next or the coming analysis. Okay, so let me return back to our whiteboard. Perfect. And let's start doing this analysis. So our circuit is like that. We have here a current source called I, and then we have our transistor, another current source here with P times I, and this is the second transistor. We have here a direction to indicate that this is a PNP transistor. And as you can see, this is a schematic. We have this schematic. So now this is VPE1, and this is VPE2, and this is plus, and this is minus, and this is delta VP, as you can see. Okay, so before going to this schematic, let me make something different. Now we have agreed that this structure should behave like a diode. This is what we agree on. When you have your BGT transistor, your basic BGT transistor, and this is here. And once you connect the collector to the base, so this is a collector and this is a base. Once you make this, you deactivate the p-n junction between the base and the collector, and the remaining p-n junction is between the base and the emitter. So this is basically an equivalent for a p-n junction. So accordingly, the current flowing here, which we call it in electronics the IC or IE, we can assume that both are typically equal. So the current flowing here is mainly a diode current. So you can say that I equals I saturation times e power V over VT minus 1. I'm sure that you remember this equation. This is a very standard exponential equation for a BGT. So I is the current flowing of the diode, which is in our case is IE. IS is called the saturation current. Exponential, the V is the voltage applied on the diode, which is typically VCE, which is the same as VPE, over VT, which is the thermal temperature, KT over Q, minus 1. So I can write it. IE equals IS E powers VPE over VT minus 1. So you can write it in this way. Okay, so now this is an exponential curve, a term with VPE mostly around 0.7 and VT, which is the thermal temperature, KT over Q. Just please remember that VT equal KT over Q. So this VT over KT over Q or VT is around 25 to 26 milli-electron volt. So you are dividing 0.7 volt, or let's make it in milli. So you are dividing 700 millivolt over 25 millivolt, which means that this exponential will be to some sort of a higher magnitude with respect to the 1. Accordingly, you can say that the current flowing in the diode is approximately equals to IS e to the power VPE over VT. So this is simply a very simple equation where you can write the current flowing in the diode is equal to the saturation current exponential to the power VPE, which is the voltage applied to the diode, over VT. Great. So using the same approach, let's turn back to our schematic. When you return here to our schematic, you find that we have two diodes. The first diode has a current called I and has the voltage, which is VPE1. The second diode has a current which is called P times I and has a voltage which is called VPE2. So simply, we can write an equation for each of these two transistors or between quotation for each of these two diodes. So for the first diode, the one on the left, we can say I equals IS exponential E VPE1 over VT. So this is an equation for the first diode. By very simple mathematics, by putting this IS in the left-hand side in the denominator and multiplying both sides by ln, you can find that VPE1 equals to VT ln I over IS. Or in other words, you can say that VPE1 equals KT over Q ln I over IS. So this is a very simple equation to express the voltage VPE1 as the function of temperature and the current flowing in the transistor. Okay. Following the same procedure, we can write another equation for VPE2. So starting with the current in the VPE2. So please remember, let me use the previous slide, that in the second transistor, the transistor into the right, the current flowing in the transistor is P times I, not only I. So in this case, you can say that P times I equals to IS exponential e to the power VPE 2 over VT. Just a hint, please take care that we use the same IS for both transistors or for both diodes, because typically we are considering that these two diodes are identical of the same material under the same doping conditions. And we use the same VT for both diodes because simply both diodes are exposed to the same temperature. So by doing the same approach, you can find that VPE 2 equals to VT, which is KT over Q, ln P times I over IS. Now you have an equation for VPE2. And you have another equation for VPE1. And we define in the circuit, as you can see, what's called a delta VPE, which is VPE2 minus VPE1. So you can simply subtract VPE2 from this VPE1 to get what's called a delta VPE. So delta VPE is equals to KT over Q ln P times I over IS, which is identically VPE2, minus KT over Q ln I over IS. As you can see, KT over Q is a common factor. Whenever you have two ln subtracted, then you can make it in terms of a ratio. So you can reach a general formula, say that delta VPE equals to KT over Q ln P. This is a very interesting output because now you have a variable in the circuit or an output in the circuit, which is delta VPE, which is only function in temperature. Why I say only function in temperature? Because K is a constant, Q is a constant, and P is a design constant parameter. So for example, whenever you start your circuit, you put I equals 1 ampere and B times I equals 2 amperes, so P equals 2. This is a constant. Accordingly, you have this direct relation between temperature and delta Vp. And the slope of this direct relation is K over Q ln P, which is typically your sensitivity. So whenever you change the temperature by 1 degree Celsius, the variation in voltage will be equals to K over Q ln delta P. Herein, it comes to us that delta P. So now let's go to the secret beyond this P parameter. Why we insert this P? You can mathematically address the importance of this P when you see this equation, because this simply, if we have this P equals to 1, then this equation will vanish and there will be no temperature dependent on this delta Vp. You can understand it from a circuit point of view in a very simple way. When you put here P equals to 1, which means that I is equivalent to I, which means that these two transistors become identical in terms of operation, and this delta VBE is equals to 0. So you have to have this P exist with a value greater than 1, so that you can address the difference in the voltage, which reflects the variation in the temperature, as you see. Another importance of this P will appear in the next slide when we scale up this thermoelectric transistor. But as a conclusion for this part, you can see that from this equation that the basic circuit described in the slide is capable of getting information about temperature and transferring it into voltage variation, as you can see in this circuit diagram. So let's now go to some sort of an advanced thermoelectrical sensor circuit base. Of course, this one is another ratiometric temperature measurement using bipolar transfer. Principally, you will find that we are using somehow the same concept. So herein, we still have the same structure, the same bipolar junction transistor structure, like this one typical. And herein also, we have our two current sources with still a P ratio current sources called P to indicate the difference between them. And a very, very important parameter here, which is called R. This R, actually, E represents the area of the matter, but this R represents the ratio parameter. We introduce this R to consider the mismatching factor between these two transistors. So, principally, in this case, we assume two identical transistors. That's why we are using the same IS and the same angles of everything. But here we have a mismatching parameter called R that appear in the map. Again, we're still using the delta VPE with a positive to the right and the negative to the left. But now this delta VPE is amplified with a factor called alpha, and then multiplied by V, or then we call this VPTAT, or in another word, V absolute. And in parallel, we have a branch of a transistor. Again, this transistor is connected in a diode format with another current source called I2. And from this, we have a branch to be added to the V absolute, and the output is V reference. So we have the V absolute, or abbreviated by VPTAT, and the V reference. Let's now describe what are these V absolute and what does V reference and why we call them absolute reference. Okay, so let's now turn this two variable into mathematical equations. So I will turn to my whiteboard screen, but I would recommend that you keep the circuit on also your screen so that you can monitor my mathematical expressions with respect to this circuit schematic. So for the V absolute, we can write. Okay, I will also make it in my screen as well so that I can see it while I'm writing the equation. So we can write V absolute simply as equals to alpha times Vp. Okay, so we already know this delta VPE. We have already reached an equation for this, which is KT over Q ln V, if you remember, ignoring any mismatching factor or such. Okay, so the first equation for the V absolute. If you return back to the schematic, let me share the screen for a few seconds just to keep you engaged with the circuit. And also let me use my pointer here. So if you return here, V reference equals to what? Equal to this new V. Let's call it here, we call it VPE. So we have VPE1, VPE2, and VPE here. So this is VPE plus V absolute. Okay, so let's write this equation. So this V reference equals to what? Equals to VPE plus V absolute. Exactly. So what is this VPE? Again, let's go to the slides. I'm sorry if this causes interruption for you. So again, this is a tight configuration. So this VPE can be expressed typically the same as these two VPEs. We already drive an equation for them in terms of to the conducting current I2. So we can say that the VPE, this new branch of VPE equals to KT over Q ln the conducting current, which is I2 over IS. Now, to proceed on this mathematical version, we have to understand the concept beyond this V reference. What is the reference voltage? We know that this delta VPE is the voltage that reflects the radiation temperature. And as you can see, V absolute is just an amplification version. So we just get delta VPE and amplify them, or amplify it by some sort of amplification factor called alpha, and that's all. So still, this V absolute is still express the variation in temperature. But what is a V reference? In order to have a calibrated measurement, you should always have a reference. What is the definition of a reference? A reference is a voltage that is independent on the varying or the measuring quantity. So this delta VPE expected to vary by varying the temperature. So where is the benchmark? Where is the reference voltage at which we can compare this delta VE with respect? This is a V reference. So the target of a V reference is to have delta V reference by delta T equals to 0. So this means that V reference is not dependent on temperature. It's a constant voltage to be generated by the sensor regardless the temperature measurement. So based on this, the target is to make this equation independent on temperature. Basically, this is very challenging because delta VPE depends on temperature, and VPE also depends on temperature. So we have to make a contrast dependence so that the equivalent dependence is equal to 0. So how we can make it? Let's see. So I write now a detailed equation for V reference. So V reference equals VPE, which is K T over Q ln I2 over IS plus delta VPE or plus V absolute, which is alpha times delta VPE, which is K T over Q ln B. This is alpha because this is the amplification factor. Okay. Whenever you start to differentiate this equation, so partial V reference by partial T capital or by partial temperature, it is very difficult to differentiate these two. Maybe one of you told me, yeah, it's not difficult. We only have a temperature dependent here. So we just have the all other equation, or K over Q ln I2 over IS is the differentiation. This is of course wrong because as you know, both these two sources are or these two currents are temperature dependent. I2 is a current source, which is basically a temperature dependent, and I saturation is a temperature dependent. So we can never say that this is a totally temperature independent. So in order to make it easy, we just write partial V PE by partial T. So this is the differentiation of this, whatever it is. Plus, here life is more easy because P is a constant, alpha is amplification is a constant. So here alpha K over Q ln B. Now, is it possible to make this equation equal to 0? Let's see. P is already adjusted. K over Q is a constant. But we still have a new design parameter, which is alpha. So you can easily put alpha equals to negative partial VPE by partial T capital times Q over K ln B. If you put this alpha in this value, accordingly, you can have a V reference which is independent on temperature. Let's see this into graphs. So let's do it here. This is the targeted alpha. If alpha equals to negative partial VPE by partial T Q over K ln B, and here he introduced in the reference this R factor, I will return back to consider it. So we will have this. Let's see. We have a VP, this VP, and VPE starts to decrease whenever the temperature increases. So when the temperature increases from negative 20 to 173, which is 0 absolute Kelvin, to 130, this is VPE decrease. On the other hand, you adjust alpha so that the V absolute, which is alpha times delta VPE, increases in the same ratio as VPE decrease. So this is the slope of decreasing of the VPE, and this is the slope of increasing of delta VPE times alpha. So as you can see, this is just delta VPE without alpha, and after amplification, this slope increase, as you can see. Now, as the V reference is the addition of these two components, the equivalent V reference is constant. So the equivalent V reference is still is still not a function in temperature, as you can see. And herein we consider it as a reference voltage. And the most famous term or name for this voltage is the band gap voltage. Those who are working in energy management electronics and analog electronics can tell you a lot about this reference voltage. It's a concept of having a voltage which is temperature independent by adding two voltages. Each of them is individually temperature dependent with negative sign, so that the equivalent voltage, or what we call it here, the reference voltage, become a temperature independent voltage. And we call it the band gap voltage simply because it is equals to 1.2, which is typically the same value like the band gap for silicon, the most famous material in electronics. That's why we call it a band gap voltage. So this is simply reference. Now, in your temperature sensor, you will have two signals. The first signal will indicate a reference voltage, which is totally independent on temperature. And the second signal indicates the variation in temperature through this delta VPE after an amplification with an amplification factor called alpha. So we have this amplified signal here. Now it's time to process this using ADC and any other processing techniques in order to transfer it into a digital signal and then transfer it over communication link and so on. So this is an example of a real circuit integrated sensor for temperature. Let's now turn to a second type of a sensors, which is the light sensors. Or in other words, we can call it a photodetector, because all of us know that light, or the photon, is the quanta of light. So whenever you need to measure or to detect light, you are simply seeking for a photon detector to detect photons. Again, let's go to the same slide. If you remember, whenever we consider the temperature, we consider the p-n junction as a basic way to use semiconductor to sense temperature. Again, when we consider light, we are going to consider the same concept here. Again, a p-n junction, but now the source of carrier generation, or between quotations, the source of non-equilibrium, will not be temperature, it will be light. Let's describe the process in a very easy manner. This is a p-type material, this is an n-type material. Here we are assuming that the light will be exposed to the p-type terminal. So whenever you have already some electrons here, whenever you have a photon here, but there is a condition. What is the condition? The condition is that this photon should have an energy greater than or equal the band gap of the material. So whenever we are considering silicon, for example, with an energy band gap of 1.12 electron volt, then we should have a photon with energy greater than or equal this 1.12 electron volt, which is typically an ultraviolet, visible, or near infrared photon. Then this photon will be captured. Electron hole pair generation will occur whenever an electron generated here with the existence of this drift due to the p-n junction, then the electron will start to move to the other side. Whenever we have a carrier, a free carrier moving, then we have a current. The higher the number of photon absorbed, the higher the electron will be generated, will be transported to the other side, the higher the current. However, in electronics, my dear students, we call this current as a minority current. Why we call it a minority current? Because simply these electrons are in the p side region. as you know, P side is a place where holes are dominating. So whenever electrons in the P side are considered, these electrons are a minority carrier. So that's why we call this a minority carrier. And herein, the current proportional to the light is the minority carrier current. The higher the minority carrier current moving, the higher the light you are detecting. Maybe we are going to recall this back when we go to the chapter for energy harvesting, because one of the most famous energy harvesters are light harvesters, which is somehow based on the same concept by a way or another. So we will return back. That's why I didn't consume a lot of time considering this light sensors. Again, if you remember, we consider that we are considering sensor on chip. So still you can build your light detector or light sensor on a chip. This is a model for a light sensor in a chip. Now, this is a termination for the first part of the first chapter. In the next part, inshallah, we are going to consider the biosensing using organic field effect transistor. Thank you very much for your concentration and see you in the next lecture, inshallah. Thank you.